Okay, this will be our first video since starting the new material on repetitive motion or periodic motion. And something we started with was just the idea that the force was that due to a spring. And so F is minus kx. That was one of the things that we dealt with, and we extended that to making the minus kx equals ma. That's a little sloppy, but and then continuing on to realizing that the acceleration is the second derivative with respect to time of the position. And so what we've got so far is based on this equation. And let's look into that. This is a differential equation. It's a relation between the derivative of something and the object itself, or the quantity itself anyway. The solution to that, that's the most general solution, is a cosine of kx. Whoops. Cross that out. I'm thinking of something else. X equals a cosine of omega t, and we tossed in a variable here, or actually a constant here, that we call the phase constant. And that just depends on when you happen to start the time. And so that's part of the equation that we have here. Now, the solution that could just as easily work is a sine of omega t plus phi. You'd get the same sort of behavior. You'd have a different value for phi, but we'll just go with that because that's what the textbook chose. Some things that are built into this is, one, that omega ends up equaling the square root of k over m, and we'll call that the angular frequency. Built into this is also omega is equal to 2 pi times the ordinary frequency, and the frequency is how many times per second this repetitive behavior will occur. And then, because there's a relation between frequency and period, that the frequency is the reciprocal of the period, we could also write omega equaling 2 pi divided by the period. And we're going to work with these different mathematical relations, really pretty much this one, these, and this, and see what we can do with this. And so I'll do a few problems that are fairly simple with respect to this. And then we're going to do something where we'll start considering energy in this behavior and see what comes out of that. So the first problem, this is out of the textbook we're using this quarter. In a physics lab, you attach a 0.200 kilogram air track glider to the end of an ideal spring of negligible mass and started oscillating. Now, the situation here, you could kind of make a sketch of it. If this represents the air track, it's something you can have where you have all these little holes with air blowing through them, and things move along on the surface of it without friction. So at one end, you've got some kind of a firm support, and then you have this spring that's attached to this glider that moves back and forth on the air track. We used to have some air tracks. They had kind of a, if you look down the length of it, it had a top that looked like this. They were big and took up tons of room in the storeroom, and the little holes blew the air out of the thing, blew the air out of the thing in this direction, and there were zillions of those little holes on there. And so if you set the glider on here, which was generally shaped, I don't know, kind of like this anyway, the glider would fit on there, the air would support it, and you could just give it a shove and it'd move back and forth very easily. And they were okay, but in this case, we're just going to have this thing going back and forth here. So we know what the mass of the glider is, and we know that it first goes through the equilibrium position, and then the second time it goes through there is 2.60 seconds later. Well, it helps a little bit to understand what's going on here. And if we make a graph of the position of this thing, not getting very straight stuff, but if we just had a cosine function, and maybe I won't include 0 over here. Maybe I'll just start making the graph here. But the motion looks like that when you grab it. And actually, I can show you real quickly a graph that would show that. Here's a couple of cosine waves on there, and I'll talk about those a little bit later, but the object that's oscillating, moving that, will spend as much time below the horizontal axis, which maybe you can't see so well. It's not very dark in there, but they spend the exact same time amount above that equilibrium position as below the equilibrium position. So let's come back to the thing that we're solving here. Anyway, maybe here's the first time it goes through the equilibrium position. Here's the second time it goes through the equilibrium position. And it's 2.60 seconds between these two. Well, it spends just as much time in a cycle above that position. And so all the way from here over to here would be one period of the motion of the thing. And so if 2.60 seconds is the time between these two, the whole period is going to be twice that. And so something we can say right off the bat is that the period is going to be 2 times 2.60 seconds, or 5.20 seconds. So now we know that. And if we know that, then we can figure out what omega happens to be. Omega is 2 pi divided by the period. So 2 pi divided by 5.20 seconds, and with 3 significant figures on there. We'll have that omega is 1.21. Now, various units work for omega. In this case, you could think of the 2 pi radians on top. A radian is just a placeholder word, gives us something to put on top. Or you can also write this as 1.21 seconds to the minus 1. And so either one of those things. And this is a handy notation at times. You have to remember that it's a per second, but it's 1.21 radians per second anyway on that thing. So what else can we figure out from this? Let's see. Oh, we're supposed to find the spring constant. Well, omega is also equal to the square root of k over m. And now that we know that omega is 1.21 seconds to the minus 1, we can just square both sides of this and then solve for k. So this one isn't too terrible a problem. So if I square both sides, on the left side, I'd get k over m. When I square 1.21 seconds to the minus 1, I get 1.46. And that's seconds to the minus 2. And whoops, minus 2. Say one thing and write another. Anyway, k is going to equal that mass times that thing, the 0.200 kilograms times 1.46 seconds to the minus 2. And I get 0.292. And that'd be kilograms seconds to the -2, which is kilograms over seconds squared. And we've done this a few times now, but I'll do it again here. If you multiply that by 1, which is meters over meter, oh, this M stands for the mass, this M stands for meters. Anyway, if you group 3 of those units together, kilogram meter per second squared, that's a Newton. And so we can also write this spring constant as 0.292 newtons per meter. And it's easier to picture this being a spring constant when it's written that way, but the kilograms per second squared work just fine times. So we'll probably hop back and forth between using these things. Okay, so there's a relatively simple problem, but you did have to use some of these relations that are brand new to you. So it's not going to be painless doing that. So let's go back to that expression that I have of, hopefully we're looking at this now. I can change some things on this graph. Actually, I've got 2 cosine graphs on here. One is just the cosine of omega t, which is a cosine function without a phase constant. That's the blue curve here. And the other is the cosine of omega t plus phi. Actually, I've got a negative value for phi in here, but let's see. Yeah, I have a negative value, and I can make that 0 easily enough. In one of these cells, I've got something that multiplies a step size that I have in here. And the step size that I used in graphing this stuff, but I'm also using it in the phase constant, is pi divided by 12. And so if I put a 0 in here for the step size, what happened, the red curve is still there, but it's directly underneath the blue curve, and you can't see it. If I just put in a step size of pi over 12, so I make the phase constant equal to that. And I don't know if you can see my cursor or not. I wonder if I could draw on here. Never tried this. I should probably not try that at this time. Anyway, there's the phase constant up there, but if I toss in the phase constant, now this is a negative phase constant, so it'd be the cosine of omega t minus pi over 12 is what the red graph did. And you can see with a negative phase constant, it shifted that entire red graph over to the right, out from underneath the blue graph. And if I put a 2 in there, give it another tick, takes just a little bit, but it's moved over there, jump it up to 4, and it moves a bit farther. If I put in a 6, it'll have a phase constant of 6/12 of pi, which is 1/2 pi. And something that you can see now is that the peak of the red graph is occurring where the blue graph is at 0. So it's shifted it by that far. But anyway, a negative phase constant moves things to the right. Now, in this over here, the actual calculation of the phase constant and the value of it, I've got built into it a minus sign. But if I go back to 0 for the multiplier, and I'm going to go into this thing and get rid of the minus sign. Actually, I'll just delete the minus part of it and multiply it by 1. All right, still get 0, but now I can do a 1 over here. Now it's got a phase constant of 1/12 of pi. And you can see the red graph has moved out from underneath the blue graph, but to the left this time. So a positive phase constant shifts it to the left. And I can just go through tossing some numbers in here. There's a 2 shifted farther to the left. There's a 4 shifted farther to the left as well. And a 6 shifted farther to the left like that. Shift it by pi. This is something that's not that interesting now, but in a little bit of time, we're going to start considering the superposition of waves where 2 waves are added together. And if the 2 waves that are added together happen to be called out of phase by pi, where one of them is shifted with a phase constant of pi, and they're harmonic waves or sine waves like this, if you imagined adding these 2 waves together, they cancel each other out. And so that's something that happened with waves, that they cancel each other out. It's an interesting part of this study. Okay, let's go back and solve some more problems. Okay, back to solving problems here. Here we have a mass m naught attached to a spring and hung vertically. So that's what you did in the lab. The mass is raised a short distance in the vertical direction. So after it's attached to this mass, it was allowed to settle in some equilibrium position. And then just as you did in the lab, you lift the mass a short distance and let it bounce up and down then. So, and it oscillates with a frequency f naught. So something that we could write off the bat here is that omega, which is 2 pi f naught, is going to equal the square root of the spring constant divided by that initial mass that was on there. Now, if the mass is replaced with a mass 9 times as large and the experiment is repeated, what would be the frequency of oscillations in terms of f naught? Okay, well, it's asking about the frequency. Let's go ahead and solve this for the frequency. It's not going to be a tremendous thing. We just divide both sides by 2 pi. So here's something that you can get out of this stuff. Okay. Well, then we replace this with a mass that's 9 times as large. How's the frequency going to change? Just about do this in your head, but the new frequency will equal 1 over 2 pi times the square root of k divided by 9 m naught. And way back in algebra class, you may have learned how to simplify radicals and things like that. If I just do that here, I'll still have the 1 over 2 pi out front, but I can split this radical into 2 parts. One that is a radical with 1 over 9, and one is a radical with k over m naught. And then if I take this 1/9 and move it over there, and I can actually take the square root of 1/9, it's 1/3. The new frequency is going to be 1/3 of, I'll take the 1 over 2 pi and move it back there. Remember, you can multiply in any order you like. So we'll have 1 over 2 pi times the square root of k over m naught. And this stuff here is the original frequency. So we end up with 1/3 of f naught. So when you make the mass 9 times as big, you end up with an oscillation frequency that is only 1/3 what it was before. We didn't check this out, but in the lab, you tested a 50-gram mass hanging from the spring, and you also did a 450-gram mass, which is 9 times as much. And if you compared your data, you might have seen that the new frequency was 1/3 of the old one, or the new period would be 3 times as long as the old one. You were measuring periods. So you might look at your data and see how well that met up. Okay, here's another one. We have a 0.500 kilogram mass suspended from a spring, and it oscillates with a period of 1.50 seconds. How much mass must be added to the object to change the period to 0.200 seconds? Well, there are two ways to do this. In this case, we know the mass that we've got on there, and we know the period when it's just oscillating there. From that, we could figure out the spring constant of this thing. And that's kind of the brute force method. And I'll do it that way. But then I'll show you maybe a little quicker way to do that. And so if we remember the period is the reciprocal of the frequency, we could say that 1 divided by the original period, I'm going to call it T naught, and M naught, the original mass, just to continue with that notation. But 1 over T naught would equal the original frequency, and that's 1 over 2 pi times the square root of K over M naught. And if I square both sides of this and this, I get 1 over T naught squared is going to equal 1 over 2 pi squared is 2 pi quantity squared is 4 pi squared. And then I just have K over M naught there. And if I just solve that for K, I'll have K is equal to 4 pi squared M naught over T naught squared. And they told me what the original mass was and what the original period is. So this is just a little bit of arithmetic at this point. 4 pi squared times 0.500 kilograms and divided by the 1.50 seconds. A little bit of work. And I get, for the spring constant, 3 significant figures, 8.77, and I'm just going to leave it as kilograms per second squared here on this one. And then it asks, how much mass must be added to the object to change the period to 2.00 seconds? Well, now we've got a new period, and we want to know how much mass. We know what the spring constant is, so we can work with this original equation. And actually, I think I'm going to, well, I'll just leave the period where it is, and we can do a little bit of work with that. The new period is 2.00 seconds, and that will equal 1 over 2 pi times the square root of our spring constant, same spring, and on the bottom, we have some new mass that we don't know. So this isn't a bad thing to solve. Square both sides, and I'd get 1 over, I can do that in my head. It's 4.00 seconds squared is going to equal 1 over 4 pi squared times 8.77 kilograms per second squared divided by the mass. And if I multiply both sides by 4.00 seconds squared over m, nope, how about m over 4.00 seconds squared. No, 4.00 seconds squared. Yeah, m over... Ah, all right. It's early in the morning. You can probably tell from my voice. How about 4.00 seconds squared times m? All right, I'll do that. And on the left side, what I'll be left with is just m. And on the right side, the m's will go away, and I'll have 4.00 seconds squared over 4 pi squared times 8.77 kilograms per second squared. Okay, so the mass ends up being whatever the product of all that stuff happens to be. And I get 0.889 kilograms. That's the new mass, the added mass. This is going to equal m naught plus some change in mass that we added on to there. And m naught was the 0.500. So the delta m is going to be this minus 0.500. Which is 0.389 kilograms. Okay, that was a brute force method, and it's not too bad, but there's a slightly more, I don't know, it's just a different way that I'll show you now. We'll be dealing with the same problem, so I'm just going to take this. I need a weight. Tape dispenser, perfect weight. Okay. Here's the thing. I've got, let's see. Yeah, I'll go with that equation. 1 over T naught is going to equal 1 over 2 pi times the square root of K over m naught. And we know that T naught is equal to, let's see, 1.50 seconds. And m naught is 0.500 kilograms. Now, what I'm going to do is come up with a new period, T final. In this case, it's going to be 2.00 seconds, which is equal to a multiple of, that's 4/3. Well, just go with that. T naught, well, I've already got that. That was 1.50 seconds. If I divided T final by T naught, I'll be dividing 2.00 seconds by 1.50 seconds. And that ratio happens to be, whatever it happens to be, 4/3 actually, which can be written as 1.33. So T final is equal to 1.33 T naught. I wrote it as 4/3 when I actually went and solved this thing, and then remembered I had 3 significant figures on that. We can just go with that. Okay, now that T final is going to equal 1 over 2 pi times same spring constant, but it'll be divided by some m naught plus delta m. And I'm going to take, whoops, this isn't right. I have to flip this upside down, this whole fraction, in order to do this. So this would equal 2 pi times the square root of m naught plus delta m divided by k. Okay, that's what T final is equal to. I'm going to take this, my original equation was T naught was equal to 2 pi times the square root of m naught over k. Okay, so this is a long stretch between the equal signs, but that's what I've got. I'm going to take this top equation and divide it by the bottom one. T final over T naught is going to equal 2 pi times the square root of m naught plus delta m over k divided by 2 pi times the square root of m naught over k. But I already know that T final over T naught would just equal 1.33. So this will be 1.33, or I can write that, I'm going to write it as 4/3 because I can do a lot of stuff in my head on this thing. Okay, well, in this expression, that simplifies quite a bit. The k's actually pop out of this one, and I'll have m naught plus delta m over m naught on there. And that's what I need to solve, and I need to solve it for delta m. Okay, so I'll square both sides here, and I'll get 16/9 is equal to m naught plus delta m over m naught. And let's see, if I multiply both sides by m naught, I'd get 16/9 m naught is equal to m naught plus delta m, or delta m will equal 16/9 m naught minus m naught. M naught is 9/9 m naught. This actually ends up equaling 7/9 m naught is the delta m, which is 7/9 times, I forgot what m naught was, 0.500 kilograms. And I can keep 3 significant figures on the result, and I get 0.389. Let's see. Which is exactly what I got the other way. So that's just a little bit of a tricky way to do it. Sometimes you can bypass having to find that thing. It may look like more work, but I actually made it more work than it had to be. Anyway, there's a few basic problems. After this, I'm going to record, and I'll probably do this live today, record a video where we start looking at energy considerations for simple harmonic motion. Stop this recording here.